Deep Learning: Guide to Machine Learning and Artificial Intelligence. Written by David Feldspar. Narrated by Jason R. Gray. How deep learning algorithms are changing lives and business. Smart computers aren't science fiction. They are now science fact. In 1996, Deep Blue, IBM's chess-playing supercomputer, beat Grandmaster and World Chess Champion Garry Kasparov under standard tournament rules for the first time. Kasparov was not pleased. In the subsequent decades, chess players at every level have had a growing variety of chess machines to play against and hone their skills. Most of them still lose, even against a chess engine running on a smartphone. The power of these computers is a demonstration of Moore's law in action, the proposition that chip performance would double every 18 months. Chess machines have ever more processing power and can crunch numbers and data at ever greater speeds, and use enhanced processing power to search through all possible future moves to find the best next one. But until now, the way they play chess has not changed. By the time IBM made adjustments to Deep Blue, its brute processing power meant it could evaluate 200 million separate positions every second, and had earned a position on the top 500 list of the most powerful supercomputers. Kasparov was realistically looking at no more than 5 positions a second. But he kept up with the computer even if he didn't win the match. But all that has changed, and the consequences reach much further than the esoteric world of chess grandmasters. Researchers at Imperial College London have created an artificial intelligence machine called Giraffe that has taught itself to play chess. Using deep learning, the new machine evaluates the board in the way that humans do. Rather than use brute strength to assess all possible positions, it uses AI to evaluate the next tricky move. Deep learning algorithms are filtering through to all kinds of areas. Facebook can automatically tag you in a picture because deep learning algorithms have taught it the difference between you and your best friend. Amazon and Netflix use deep learning to make more accurate suggestions for books, films, and music you might like. And LinkedIn finds possible contacts with almost spooky levels of accuracy, all because of deep learning. These are the most obvious examples of deep learning in play today, but they're just the start. Consider self-driving cars as an example. In order to work safely, the car has to observe the world around it and process information as a human does. It needs to be able to distinguish between a tree and a traffic light. But it is impossible to imagine a situation in which a human could program a car to identify every single type of tree that it might encounter in every season and at every light level. A deep learning algorithm, however, can look at millions of images without tags or text, and through sophisticated classification of data and context, learn the concept of a tree, and so identify one in real life. What separates deep learning from pattern recognition and previous analytic capabilities is its ability to learn, understand, and apply context. One of the more obvious examples is in the area of linguistics. As anyone who has attempted to learn a foreign language knows, there's more to it than translating vocabulary word for word. Meaning often comes from idiom and colloquialisms, very precise word use, and even pronunciation. Online translation services struggle with these at the moment, but machines can learn to speak, read, write, and simultaneously translate any number of languages and alphabets. There is a similar approach in medical science, where deep learning algorithms can perform advanced diagnostics and prognosis for some of the most obstinate diseases, and even accurately predict a patient's lifespan, all from understanding the context of the images in front of them. What's interesting about this, and the language example, is that developers of the algorithms need have no medical or linguistic knowledge themselves. In effect, deep learning removes the limitations of human capability from the development of technology. Computers can learn to do things that humans can't do. Chess experts taught Deep Blue to play chess. Giraffe teaches itself. A computer can speak Chinese even if its programmer can't. Naturally, this presents opportunities as well as challenges. Health outcomes could be improved everywhere, particularly in areas where doctors are rarely available. International relations, in both the political and commercial sphere, become easier and smoother. At a business level, deep learning will create far greater understanding of who customers really are. In the area of finance, deep learning will improve techniques for detecting and preventing fraud and scams. In retail, truly personalized services could become the norm. Improved diagnostics could be applied to physical or remote infrastructure as well as human bodies, for more efficient and safer manufacturing or energy generation, for example. In this world, advanced programmers and data scientists are going to command a premium. Deep learning algorithms are changing our reality and becoming more commonplace by the year. Computers that can read, write, speak, and learn are going to feature in all kinds of spheres that were previously considered immune from the automation trend. Top 5 Machine Learning Use Cases for the Financial Industry. The financial industry has always been one of the most powerful influencers and consumers of technological innovation. The banks were the first to leverage trains for postal services, introduce fire alarms, and CCTV surveillance. Now they do the same with machine learning. Machine learning, or ML, as a part of the greater artificial intelligence, or AI, industry, evolves rapidly. While it has reached several significant milestones already, like Deep Blue defeating Kasparov 20 years ago, or Google's DeepMind algorithm AlphaGo defeating the Go champion Lee Sedol in 2016, or Google's algorithm trained to tell cats from dogs and used to identify skin cancer, business needs more practical, and yes, by practical we mean feasible, ways to apply ML in daily operations. This time has come, and today we will tell you of top 5 machine learning use cases for the financial industry, so you know why venture capitalists and banks invested around $5 billion in AI and ML in 2016. Customer self-service portals. Call centers are a thing of the past, as the generations of computer-savvy people enter the banking world. Both millennials and Gen Z prefer customer self-service portals and mobile banking through their smartphones. More than 44% of U.S. consumers prefer interacting with chatbots, not with human representatives. Deploying ML algorithms to serve as chatbots might allow saving up to $27 billion in salaries in insurance and financial sectors. This also excludes the human error factor, as ML algorithms never sleep, never yells at the customer, and constantly learns and only becomes better over time. Risk management in banks and financial institutions. Risk management is another field where implementing ML can lead to dramatic improvement of results. When the algorithm is able to analyze the whole variety of incoming data, both internal from the company business flow and external, like customers' search queries and social interactions, both beneficial or potentially dangerous trends can be recognized and exploited or mitigated. Yet another brilliant research on the future of risk management in banks from McKinsey states, risk management is crucial for success and financial health of the banks and other institutions. ML is the key element, allowing to evaluate all the factors to make a well-grounded decision and every new piece of information processed by the algorithm makes its predictions more accurate. Compliance checks. Many regulatory documents, like the USA Patriot Act, require a thorough and in-depth analysis of the financial background for many customers in many types of transactions. This means every financial institution has to employ a compliance team that has to constantly analyze and update a huge pool of information regarding their customers and prospects. Add the splits, mergers, and acquisitions into play, and you will clearly see why this is a hell of a job. Implementing ML algorithms can help the compliance department direct all the influx of data from various disparate systems and sources to a centralized storage to be processed, stored, and exploited efficiently. This will bring the customer screening to a much higher level. Credit Portfolio Management, or CPM. Monitoring the health of credit portfolio is equally, if not more important, to checking the background of the prospects. Leveraging the power of machine learning for data analytics allows for a much more precise predictive and prescriptive analysis. This will help predict what customers are at high risk for canceling their deposits or defaulting on their loans. As a result, the bank executives will be able to intervene and prescribe a much more personalized approach, keeping the credit portfolio healthy and drastically reducing the percentage of irretrievable loans. Yet another McKinsey report describes the growing role of AI in retrieving valuable insights from the unstructured data and the benefits it brings for banks. Robo-advisors for wealth management. Being wealthy doesn't always mean being well financially educated. People often prefer delegating their wealth management to trusted financial institutions. When all the data about such fortunes, along with all the transactions and events in various important fields, is processed by a robo-advisor, the consulting financial structure is able to make swift actions. Such actions might include selling dangerous assets or buying cheap once the opportunity arises, thus ensuring optimal allocation of the customer's resources and all-around good performance of the assets. BlackRock, one of the world's leading investment management funds, has published a detailed report regarding the efficiency of employing robo-advisors for asset management. Concluding thoughts. Financial institutions have to follow the latest technology to secure their bottom line and provide the best service to their customers. About a decade ago, offering an online service was the way to gain a competitive edge. Around 5 years ago, a mobile app became an essential component of a good offering. Nowadays, employing an AI algorithm is what can push the business ahead of less tech-savvy competitors. Machine learning promises to shake up large swaths of finance. In fields from trading to credit assessment to fraud prevention, machine learning is advancing. Machine learning is beginning to shake up finance. A subset of artificial intelligence, or AI, that excels at finding patterns and making predictions. It used to be the preserve of technology firms. The financial industry has jumped on the bandwagon. To cite just a few examples, heads of machine learning can be found at PwC, a consultancy and auditing firm, at JP Morgan Chase, a large bank, and at Man GLG, a hedge fund manager. From 2019, anyone seeking to become a chartered financial analyst, a sought-after distinction in the industry, will need AI expertise to pass his exams. Despite the skepticism of many, including, surprisingly, some quaint hedge funds that specialize in algorithm-based trading, machine learning is poised to have a big impact. Innovative financial and technology firms and a few nimble incumbents have started applying the technique to everything from fraud protection to finding new trading strategies. promising to upend not just the humdrum drudgery of the back office, but the more glamorous stuff up front. Machine learning is already much used for tasks such as compliance, risk management, and fraud prevention. Intelligent Voice, a British firm, sells its machine learning-driven speech transcription tool to large banks to monitor traders' phone calls for signs of wrongdoing, such as insider trading. Other specialists, such as Accelerate and Kinetica, offer banks and investment firms near real-time tracking of their risk exposures, allowing them to monitor their capital requirements at all times. Machine learning excels in spotting unusual patterns of transactions, which can indicate fraud. Firms ranging from startups such as Feedzai for payments or Shift Technology for insurance to behemoths such as IBM are offering such services. Some are developing the skills in-house. Monzo, a British banking startup, built a model quick enough to stop would-be fraudsters from completing a transaction, bringing the fraud rate on its prepaid cards down from 0.85% in June 2016 to less than 0.1% by January 2017. Natural language processing, where AI-based systems are unleashed on text, is starting to have a big impact in document-heavy parts of finance. In June 2016, JP Morgan Chase deployed software that can sift through 12,000 commercial loan contracts in seconds, compared with the 360,000 hours it used to take lawyers and loan officers to review the contracts. Machine learning is also good at automating financial decisions, whether assessing creditworthiness or eligibility for an insurance policy. Zest Finance has been in the business of automated credit scoring since its founding in 2009. Earlier this year, it rolled out a machine learning underwriting tool to help lenders make credit decisions, even for people with little conventional credit scoring information. It sifts through vast amounts of data, such as people's payment history or how they interact with a lender's website. Lemonade, a tech-savvy insurance startup, is using machine learning both to sell insurance policies and to manage claims. Perhaps the newest frontier for machine learning is in trading, where it is used both to crunch market data and to select and trade portfolios of securities. The Quantitative Investment Strategies division at Goldman Sachs uses language processing driven by machine learning to go through thousands of analyst reports on companies. It compiles an aggregate sentiment score based on the balance of positive to negative words. This score is then used to help pick stocks. Goldman has also invested in Kensho, a startup that uses machine learning to predict how events like natural disasters will affect market prices based on data from similar events. Quantifiable progress. Quant hedge funds, both new and old, are piling in. Castle Ridge Asset Management, a Toronto-based upstart, has achieved average annual returns of 32% since its founding in 2013. It uses a sophisticated machine learning system, like those used to model evolutionary biology, to make investment decisions. It is so sensitive, claims the firm's chief executive, Adrian Develos-Franklin, that it picked up 24 acquisitions before they were even announced, because of telltale signals suggesting a small amount of insider trading. Man AHL, meanwhile, a well-established $18.8 billion quant fund provider, has been conducting research into machine learning for trading purposes since 2009, and using it as one of the techniques to manage client money since 2014. So it seems odd that some prominent quant funds are machine learning skeptics. Martin Lueck of Aspect Capital finds the technique overrated, saying his firm has found only limited useful applications for it. David Siegel, co-founder of 2 Sigma, a quant behemoth, and David Harding of Winton Capital have also argued that the techniques are overhyped. In other fields, however, machine learning has game-changing potential. There is no reason to expect finance to be different. According to Jonathan Maskey, a machine learning fund manager, years of work on rules-based approaches in computer vision, telling a computer how to recognize a nose, say, were swiftly eclipsed in 2012 by machine learning processes that allowed computers to learn what a nose looked like from pursuing millions of nasal pinups. Similarly, says Mr. Maskey, a machine learning algorithm ought to beat conventional trading strategies based on rules set by humans. The real vulnerability may, in any case, lie outside trading. Many quant funds depend on human researchers to sift through data and build algorithms. These posts could be replaced by better performing machines. For all their professed skepticism, 2 Sigma and its peers are busy recruiting machine learning specialists. How machine learning is putting an end to financial crime. The problem is one of the most pressing challenges faced by the industry, but there is a solution. The financial industry is built on data, and banks are fast realizing the potential it has to improve the experience of their customers, create efficiencies, investigate new markets, and manage risk. International Data Corporation, or IDC, estimates that banks spend almost $17 billion on big data and business analytics solutions in 2016, and this number is only set to rise as technologically driven startups like Monzo eat into their market share. While banks are systematically collecting data, however, analyzing the unfathomable amounts they have at the pace required in today's fast-moving world is a challenge beyond the scope of humans. In order to analyze their data as systematically as it is collected, banks are having to turn to machine learning algorithms across the spectrum of their operations, and it is a technology that will fundamentally change banking, making it unrecognizable to today's. This will happen in myriad ways. In a recent Baker McKenzie survey of senior executives from financial companies, 49% say they expect their firms to use AI for risk management within the next 3 years. 29% that their firms will apply AI to learn more about their clients and to prevent money laundering, and 26% anticipate AI will help with regulatory as well as risk and compliance issues. One of the most pressing challenges for machine learning to deal with in the industry is financial crime. Banks must deal with numerous different forms of fraud, and the technology is a solution for almost all of them. Firstly, it can help prevent money laundering. Banks have been obligated to assist governments in catching criminals hiding their money since the Bank Secrecy Act of 1970. Those that fail face severe punishments. Deutsche Bank, for one, was earlier this year fined more than $630 million for failing to prevent $10 billion of Russian money laundering and exposing the UK financial systems to the risk of financial crime. The New York Department of Financial Services, or DFS, also fined the bank $425 million, citing one senior compliance officer who said he had to beg, borrow, and steal to get the resources to combat money laundering. While numerous others have faced similar fines, but while it is clear that Deutsche Bank was not doing all it could, it is an incredibly difficult task to track laundered money as it spreads throughout the financial system. In a recent Dow Jones survey, nearly half of the 800 anti-money laundering professionals who responded said false positive alerts damaged confidence in the accuracy of the screening process. Analysis from 42 Data, meanwhile, revealed banks' AML divisions are wasting nearly £3 billion a year chasing these false leads. Machine learning is helping to better distinguish between these false positives and real cases. According to Rahul Singh, president of financial services at IT services provider HCL Technologies, we are already experiencing use cases of AI and advanced analytics in the anti-money laundering function, where technology is able to bring false positives down, allowing focused approaches to risk detection and avoidance. Essentially, machine learning is able to learn normal behavior from training data and identify anomalous behaviors that could indicate money laundering, such as when money is moved between suspicious geographies, rapid movement of funds between a number of accounts, or invoicing number sequences have been falsified. Where legacy systems relied on static algorithms and criteria, which basically became redundant as soon as criminals changed their behavior, which they inevitably did, machine learning is constantly learning, which means they can identify when the pattern of laundering changes and adapt rapidly. It is not just in money laundering that machine learning technology is proving to be a real boon. It can also help prevent consumer fraud. In the UK, financial fraud losses across payment cards, remote banking, and checks totaled £768.8 million in 2016, an increase of 2% on the previous year. Cybercrimes, meanwhile, are costing the global economy nearly $500 billion a year, according to the insurer Allianz, and finance is one of the most obvious targets. As the February 2016 hack of the Bangladesh Central Bank showed, customer accounts can be the most vulnerable point of entry to a bank system. The hackers used stolen privileged credentials to steal $81 million before they were caught. The threat is constantly mutating as criminals adapt to security measures and find new methods of extracting money illegally. Organizations must adapt their security countermeasures rapidly or risk massive losses, both financial and to their reputation. Machine learning can better our understanding of the transactions that flow through the bank by understanding customer behavior. This means that when any anomalies do occur, they can be automatically flagged in real time and appropriate measures taken, whether this be blocking a card or kicking someone out of a system. Nikhil Agarwal, Executive Director and Head of FCC Analytics at Standard Chartered Bank, states that there is an increasing focus across two broad categories. First, people, and second, technology solutions within financial crime risk analytics. Banks are increasingly recognizing the importance of creating a dedicated financial crime risk analytics team and are investing in talent at all levels, ranging from analysts to senior leadership roles. In terms of analytics, the focus is on technologies that apply smarter and more powerful algorithms in risk identification, and tools that improve the efficiency and effectiveness of operational workflows. One example of analytics innovation is the optimization of alert generation and the subsequent routing of these alerts to specialized investigations teams. Alerts are generated due to unusual and potentially suspicious transaction behavior and represent the first human touchpoint in a generic assessment of anti-money laundering risk. With advances in analytics, sophisticated algorithms combine unusual transaction behavior with the full history of client transactions and other behavioral patterns to form an enriched and composite view of aggregate risk. These algorithms then rank the overall riskiness of events and channel these events to the workflow queues of specialized investigations teams. This is not to say that machine learning is without flaws. It is still a technology in its infancy, and there are a number of problems. For a start, it is essentially operating in a black box, making decisions that humans are unable to understand. It will itself need regulation, which will need to tread a careful line between helping the technology do its job and preventing it from running amok, like some financial minority report. At the moment, however, machine learning in banking is still at a fairly nascent stage. Adoption is going to rise rapidly over the next year, though, and banks must look to the technology as much as possible. Machine learning algorithms for business applications. With the development of free, open-source machine learning and artificial intelligence tools like Google's TensorFlow and scikit-learn, as well as ML-as-a-service products like Google's Cloud Prediction API and Microsoft's Azure Machine Learning Platform, It has never been easier for companies of all sizes to harness the power of data. But machine learning is such a vast, complex field. Where do you start learning how to use it in your business? In this chapter, we'll survey the current landscape of machine learning algorithms and explain how they work, provide example applications, share how other companies use them, and provide further resources on learning about them. This executive overview will provide the first step in learning how to apply machine learning algorithms to make your business more efficient, more effective, and more profitable. As you read through the examples below, you might want to jot down business challenges that are analogous to the problems that these algorithms can solve. Perhaps an algorithm that predicts the occurrence of safety issues in coal mines can also be used to predict which of your restaurant franchises are at risk for non-compliance with health regulations. By the end of this chapter, you'll have an action plan of which algorithms to research further and a solid grasp of their potential to provide concrete benefits to your bottom line. Artificial neural networks. Artificial neural networks, ANNs, are biologically inspired. Specifically, they borrow ideas from the manner in which the human brain works. The human brain is composed of special cells called neurons. Estimates of the number of neurons in a human brain cover a wide range, up to 150 billion, and there are more than 100 different kinds of neurons, separated into groups called networks. Each network contains several thousand neurons that are highly interconnected. Thus, the brain can be viewed as a collection of neural networks. Today's ANNs, whose application is referred to as neural computing, uses a very limited set of concepts from biological neural systems. The goal is to simulate massive parallel processes that involve processing elements interconnected in a network structure. The artificial neuron receives inputs analogous to the electrochemical impulses biological neurons receive from other neurons. The output of the artificial neuron corresponds to signals sent out from a biological neuron. These artificial signals can be changed, like the signals from the human brain. Neurons in an ANN receive information from other neurons or from external sources, transform or process the information, and pass it on to other neurons or as external outputs. The manner in which an ANN processes information depends on its structure and on the algorithm used to process the information. Benefits and applications of neural networks. The value of neural network technology includes its usefulness for pattern recognition, learning, and the interpretation of incomplete and noisy inputs. Neural networks have the potential to provide some of the human characteristics of problem solving that are difficult to simulate using the logical analytical techniques of DSS or even expert systems. One of these characteristics is pattern recognition. Neural networks can analyze large quantities of data to establish patterns and characteristics in situations where the logic and rules are not known. An example would be loan applications. By reviewing many historical cases of applicants' questionnaires and the yes or no decisions made, the ANN can create patterns or profiles of applications that should be approved or denied. A new application can then be matched by the computer against the pattern. If it comes close enough, the computer classifies it as a yes or a no. Otherwise, it goes to a human for decisions. Neural networks are especially useful for financial applications such as determining when to buy or sell a stock, predicting bankruptcy, and predicting exchange rates. Beyond its role as an alternative computing mechanism and in data mining, neural computing can be combined with other computer-based information systems to provide powerful hybrid systems. Neural computing is emerging as an effective technology in pattern recognition. This capability is being translated to many applications and is sometimes integrated with fuzzy logic. Big data analytics. Big data generally refers to data that exceeds the typical storage, processing, and computing capacity of conventional databases and data analysis techniques. As a resource, big data requires tools and methods that can be applied to analyze and extract patterns from large-scale data. The rise of big data has been caused by increased data storage capabilities, increased computational processing power, and availability of increased volumes of data, which give organizations more data that they have than computing resources and technologies to process. In addition to the obvious great volumes of data, big data is also associated with other specific complexities, often referred to as the 4 V's: volume, variety, velocity, and veracity. We note that the aim of this section is not to extensively cover big data, but present a brief overview of its concepts and challenges, while keeping in mind that the use of deep learning in big data analytics is the focus of this paper. The unmanageable large volume of data poses an immediate challenge to conventional computing environments, and requires scalable storage and a distributed strategy to data querying and analysis. However, this large volume of data is also a major positive feature of big data. Many companies, such as Facebook, Yahoo, Google, already have large amounts of data and have recently begun tapping into its benefits. A general theme in big data systems is that the raw data is increasingly diverse and complex, consisting of largely uncategorized, unsupervised data, along with perhaps a small quantity of categorized supervised data. Working with the variety among different data representations in a given repository poses unique challenges with big data, which requires big data pre-processing of unstructured data in order to extract structured, ordered representations of the data for human or downstream consumption. In today's data-intensive technology era, data velocity, the increasing rate at which data is collected and obtained, is just as important as the volume and variety characteristics of big data. While the possibility of data loss exists with streaming data if it is generally not immediately processed and analyzed, there is the option to save fast-moving data into bulk storage for batch processing at a later time. However, the practical importance of dealing with velocity associated with big data is the quickness of the feedback loop. That is, process of translating data input into usable information. This is especially important in the case of time-sensitive information processing. Some companies, such as Twitter, Yahoo, and IBM, have developed products that address the analysis of streaming data. Veracity in big data deals with the trustworthiness or usefulness of results obtained from data analysis, and brings to light the old adage, garbage in, garbage out, for decision-making based on big data analytics. As the number of data sources and types increase, sustaining trust in big data analytics presents a practical challenge. Big data analytics faces a number of challenges beyond those implied by the 4 V's. While not meant to be an exhaustive list, some key problem areas include data quality and validation, data cleansing, feature engineering, high dimensionality and data reduction, data representations, and distributed data sources, data sampling, scalability of algorithms, data visualization, parallel and distributed data processing, real-time analysis and decision-making, crowdsourcing and semantic input for improved data analysis, tracing and analyzing data provenance, data discovery and integration, parallel and distributed computing, exploratory data analysis and interpretation, integrating heterogeneous data, and developing new models for massive data computation. Classification. Goal. The goal of classification algorithms is to place items into specific categories and answer questions like, is this tumor cancerous? Is this email spam? Will this loan applicant default? What category is this? Which demographic does this online customer fall into? Bayesian classifier. Bayesian classifiers are a simple yet highly effective classification algorithm. They are based on Bayes' theorem, which succinctly defines the probability of an event given that another related event has occurred. A Bayesian classifier categorizes data by keeping track of the probabilities that specific features and characteristics of a dataset that you believe may impact its classification accompany a specific classification. While Bayesian classifiers can be used for any classification task, they are particularly useful with document classification, especially spam filters. For instance, computer scientist and famed startup investor Paul Graham developed a simple Bayesian spam filter that caught over 99.5% of his spam while having no false positives, or non-spam emails mistakenly marked as spam. The features Graham used included the words in the emails, the email headers, and the presence of embedded HTML and JavaScript. Graham provides a nice illustration of how the spam filter works by extracting the 15 most interesting features, or the 15 features that were either the most powerful indicators of spam, a weight close to 1.0, or the weakest indicators of spam, a weight close to 0.0. The following chart organizes the interesting features in one of Graham's spam emails. Madam, 0.99, spammy. Promotion, 0.99, spammy. Shortest, 0.05, not spammy. Mandatory, 0.05, not spammy. Standardization, 0.07, not spammy. Sorry, 0.08, not spammy. Supported, 0.09, not spammy. Peoples, 0.09, not spammy. Enter, 0.91, spammy. Quality, 0.89, spammy. Organization, 0.12, not spammy. Investment, 0.86, spammy. Vary, 0.15, not spammy. Valuable, 0.82, spammy. Combining these probabilities via Bayes' rule results in a probability of 0.90, meaning the email is most likely spam. Bayesian classifiers are effective even with complex document classification tasks. A Stanford study showed a naive Bayes classifier. The naive comes from the classifier assuming every word's appearance is independent of every other word's appearance, was 85% accurate in sentiment analysis of tweets. Another study at MIT found a naive Bayes classifier could accurately categorize information in the MIT student newspaper 77% of the time. Other potential applications include authorship identification and even predicting whether a brain tumor could relapse or progress after treatment. Pros: often perform as well as much more complex algorithms, but while being easy to implement. This makes Bayesian classifiers a good first-line machine learning algorithm. Simple to interpret. Each feature has a probability, so you can see which are most strongly associated with certain classifications. An online technique, meaning it supports incremental training. After a Bayesian classifier is trained, each feature has a specific conditional probability attached to it. To include one new data sample, you simply update the probabilities. No need to go through the original dataset all over again. Very fast. Since Bayesian classifiers are simply combining pre-calculated probabilities, New classifications can be made very quickly even on large and complex datasets. Cons: can't deal with outcomes dependent on a combination of features. The assumption is that each is independent of each other, which can sometimes lower accuracy. For example, the words online and pharmacy may not normally be a strong indicator of spam in an email unless the words are used together. A Bayesian classifier would not be able to pick up on the interdependence of those two features. Conclusion: now that you're more familiar with common machine learning algorithms and their applications, what are the next steps in using this knowledge to meet your business objectives? First, identify your business needs and map them to the corresponding machine learning tasks. Want to get real-time data on whether social media posts about your company are positive or negative? That's a classification task. Want to predict what your real estate holdings will be worth next year? That's a regression task. Technology is transforming the way consumers behave, and this is most evident in the banking industry. With its capacity to learn from large datasets and establish patterns and correlations, machine learning can revolutionize banking operations. It can inject new efficiencies into tasks such as risk assessment, fraud detection, anti-money laundering, trading, and customer service, by providing instant insights, relevant recommendations, and informed decisions in real time. Such capabilities will help banks optimize operations to reduce cost, improve compliance, and increase productivity, thus leading to higher revenue. However, it is important for organizations to establish a clear vision and strategy, ensure information is openly available, and roll out change management programs to ensure successful machine learning-powered transformation. Thanks again for buying my book. If you have a minute, please leave a review. I take reviews seriously and always look at them. This way, you are helping me provide you better content that you will love in the future. A review doesn't have to be long, just 1 or 2 sentences, and a number of stars you find appropriate. Hopefully 5, of course. Also, if I think your review is useful, I will mark it as helpful. This will help you become more known on Amazon as a decent reviewer, and will ensure that more authors will contact you with free ebooks in the future. This is how we can help each other. You can look at these books too: Data Analytics, Data Mining, and Data Science for Business. Disclaimer: this information is provided as is. The author, publishers, and/or marketers of this information disclaim any loss or liability, either directly or indirectly as a consequence of applying the information presented herein, or in regard to the use and applications of said information. No guarantee is given, either expressed or implied, in regard to the merchantability, accuracy, or acceptability of the information. The pages within this ebook have been copyrighted. Decision Tree Classifier. Decision trees are perhaps the most intuitively understandable machine learning algorithm, because in essence they are flowcharts in software form. Decision trees classify items using a series of if-then statements that eventually result in a classification. A simple example: you come across a beverage at a restaurant and want to figure out what type of beverage it is. A decision tree could classify the beverage based on the results of the following questions. Is the beverage hot or cold? It's cold. Is it caffeinated or caffeine-free? It's caffeinated. Is it carbonated, fizzy? It's not carbonated. Was it made with beans or leaves? It was made with leaves. Final classification: iced tea. The key to effective decision tree is to have statements that divide the dataset well. That is, the most homogeneous the data is after each division, the better that division is. There are multiple metrics that can be used to determine how to split a decision tree. Two common ones are entropy and Gini impurity. Using an algorithm called CART, or classification and regression trees, each level of the tree is split via the attribute that causes the greatest reduction in the chosen metric. This process is repeated until further splits no longer reduce that metric and the tree is complete. A more substantive application of a decision tree could be predicting user signups. Suppose you run a subscription service and your system logs several characteristics about your users who've signed up for the free trial. Whether they've tried your interactive demo, whether they've signed up for your mailing list, how they found your website, like search engines, social media, etc., and whether they ultimately signed up for the paid version of your service. A decision tree could not only use this data to predict which new free trial users would ultimately become paying customers, but also show you the exact funnel which led them there. Perhaps it was social media to mailing list to paid subscription, which indicates your demo is hurting your conversion rate while your social media presence is bringing in paying customers. Other example applications. BP used a decision tree to separate oil and gas and replace a hand-designed rule system, the decision tree, outperformed human experts and saved BP millions. An MIT study examined how decision trees could be used to predict whether an applicant would receive a loan and whether that applicant would default. Pros: very easy to interpret and explain. Decision trees mirror human decision-making through their flowchart if-then style of splitting data down until that data is categorized. Can be displayed graphically. A decision tree is, in essence, a branching flowchart, just one that's been algorithmically tuned for optimal splits. And smaller decision trees displayed graphically can be easily interpreted even by non-technical people. Can easily use both categorical and numerical data. For example, is this car red works just as well as is the car's tire diameter between 6 and 8 inches. In other classifiers, you'd have to create a dummy variable to work around this. Can deal with interactions of variables. In the online pharmacy example that stumped the Bayesian classifier above, a decision tree could split the dataset on whether it contained the word online, and split the result by whether it contained pharmacy, ensuring that online pharmacy equals spam, while online and pharmacy equals non-spam. Cons: decision trees may not be as accurate as other classification algorithms as they have tendency to overfit the data, meaning they make excellent predictions within the dataset used to train them, but poorer predictions for new data coming in. Nonetheless, there are various methods of pruning the tree to improve accuracy. Decision trees are not an online technique, which means the whole tree must be recreated from scratch in order to incorporate new data, since the variables that optimally split the data could change. With larger datasets, the number of nodes on a decision tree can grow extremely large and complex, resulting in slow classifications. K-nearest neighbors. Suppose you had a fairly rare baseball card that you wanted to sell on eBay. How would you determine a good selling price? You may check what that card or similar card has recently sold for and price your card in that range. That's essentially how K-nearest neighbor works. It compares a new piece of data to data with similar values and then averages nearby items to predict the new data's value. Distance between data points is determined by metrics such as Euclidean distance or Pearson correlation. The K in K-nearest neighbors is a placeholder value for the number of nearest values averaged to make that prediction. The algorithm can also use weighted averages, where values nearby are weighted more heavily in determining the average. Variables may need to be scaled, for example, determining house prices using number of bedrooms and square footage. You may choose to use square footage and number of bedrooms multiplied by 1,000 in order to keep the two variables on the same scale. K-nearest neighbors can be used for predicting home prices, as demonstrated in the simplified example above, the prices of goods in marketplaces, as with the baseball card example above, and be used to make product recommendations. Pros: online technique. Like a naive Bayes classifier, K-nearest neighbors supports incremental training. Can handle complex numerical functions while still being easy to interpret. You can see exactly which neighbors are used for the final predictions. Useful if data is difficult or expensive to collect. The scaling process can reveal which variables are unimportant for making predictions and thus can be thrown out. Cons: requires all training data to make predictions. This means K-nearest neighbors can be very slow for large datasets and can require a lot of space. Finding correct scaling factors can be tedious and computationally expensive when there are millions of variables. Linear regression. Linear regression is a familiar algorithm that attempts to create a line of best fit for a dataset and then use that line to make a new prediction. It's the linear function, think y equals mx plus b from high school algebra, where x equals the feature and m equals the feature weight, that minimizes the error as determined by the cost function, typically the sum squared errors function. Simple linear regression only uses one variable and is thus limited in its scope, but multivariable linear regression can handle much more complex problems. Like logistic regression, gradient descent is often used to determine optimal feature weights. There are many possible applications for linear regression, such as predicting real estate prices, estimating salaries, predicting financial portfolio performance, and predicting traffic. In some cases, linear regression is used in combination with other, more sophisticated techniques to produce more accurate outcomes than those provided by any individual algorithm alone. Pros: easy to implement and interpret. Linear regression is much like logistic regression in terms of implementation difficulty, but linear equations are much more intuitive to humans than the logistic function. Cons: gradient descent trade-off. Like logistic regression, gradient descent requires a trade-off between speed and accuracy, and getting it right may take many iterations of trial and error. Not an online technique. Incorporating new data requires running gradient descent again. Dummy variables required for categorical data. Because linear regression only produces real-valued output, categorical data must be converted to real values via a dummy variable. For instance, converting red or not red to 1 or 0, where red equals 1 and not red equals 0. Logistic regression. Logistic regression is a classification algorithm that uses some of the properties of the logistic function, sometimes also called the sigmoid function, an S-shaped curve that is typified by plateaus on both edges of the function and rapid growth in the middle. Weights are assigned to features and then fed to the logistic function, which outputs a number between 0 and 1. The decision boundary determines the classification. For example, if you're using logistic regression to predict fraudulent credit card transactions, you may determine that an output below 0.5 is a legitimate transaction, while an output above 0.5 is a fraudulent transaction. Your decision boundary is 0.5. The key to logistic regression is training the model to assign appropriate weights to all the features. This first requires a cost function, which is simply a function that determines the level of error of each prediction, compared to the training example. The most common cost function in logistic regression is sum of squares error, also called residual sum of squares. Then, using a calculus technique known as gradient descent, the weights are continually adjusted until the cost function is minimized. At this point, the logistic regression classifier is optimally accurate for the prediction results in the training set. And this is the starting point for using it to predict classifications for new data. Logistic regression can be extended to data with more than two categories, called multinomial logistic regression, by using a one versus all model. To classify, say, 3 types of documents, receipts, memos, and customer mail, multinomial logistic regression would run 3 times. First, classifying documents as receipts or not receipts, then memos or not memos, and finally, customer mail or not customer mail, and combine these results to make predictions. Like Bayesian classifiers, logistic regression is a good first-line machine learning algorithm because of its relative simplicity and ease of implementation. A few example applications include analysis of sheet metals, predicting safety issues in coal mines, and various medical applications. Pros: easy to interpret. Logistic regression outputs a number between 0 and 1, which can loosely be interpreted as a probability. 0.312 could be interpreted as 31.2% chance of a credit card transaction being fraudulent. The feature weights easily indicate which features are more important in determining the classifications than others. Cons: is prone to overfitting. Logistic regression may require a fairly large training set before it can make accurate predictions outside of the training set. Not an online technique. Incorporating new data requires running gradient ascent again. Has trade-offs with gradient ascent. The faster gradient ascent determines the final feature weights, the more likely it is to miss the optimal weights. It can be sometimes difficult to figure this out, as the optimal speed versus accuracy trade-off and trial and error can be time-consuming. Dummy variables required for categorical data. Because logistic regression only produces real-valued output, categorical data must be converted to real values via a dummy variable. For instance, converting red or not red to 1 or 0, where red equals 1 and not red equals 0. Machine learning approaches as tools to accelerate drug discovery. Computational methods based on machine learning approaches are being introduced increasingly widely to screen the large number of molecules that have never participated in the drug discovery process, but which might have significant drug development potential. This chapter considers the latest advances in machine learning as applied to drug discovery. The process of drug development is time-consuming and costly. Several years are required for lead identification, optimization, in vitro and in vivo testing before the first clinical trials begin. The cost of developing a prescription drug that gains market approval, accounting for the very high failure rate, exceeds $2.5 billion. Different approaches have been developed in recent years to accelerate and improve the success rate of the early drug discovery process, including high-throughput screening technology, 3D culture screening, and tissue printing and organs-on-chips technology. A significant advancement in the process of screening was introduced over a decade ago with quantitative high-throughput screening, or QHTS, which allows the efficient identification of biological activities in chemical libraries by testing each library compound in a dose-response format. It is shown that QHTS can be successfully applied to finding new inhibitors For druggable and non-druggable targets, epigenetics modulators, deorphanization of GPCR receptors, P450 isozyme selectivity across chemical libraries, and profiling of environmental chemicals' potential to disrupt processes in the human body that may lead to negative health effects. QHTS can be used to screen large chemical libraries, producing high-quality chemical genomic datasets, which can be publicly available through sites such as PubChem. Neural networks. Neural networks make both numeric, for example, see the next section, and classification predictions by loosely imitating the way the brain processes information. In the human brain, neurons transmit information by forming connections with other neurons and transmitting electrochemical signals through these neural networks. Artificial neural networks are also more simply called neural networks or neural nets. There are many different kinds of neural networks, so to keep things simple, we'll look at just one called a multi-layer perception neural network, MLPNN. An MLPNN contains at least 3, but often more layers of neurons: the input layer, one or more hidden layers, and an output layer. The input layer consists of the data you're using to generate the prediction. The hidden layers, named because they don't directly interact with either input or final output, work on the data fed to them by the previous layers. And the output layer is the final prediction produced by the algorithm. These layers are connected by synapses, named after the corresponding structure in real-life brains that allow electrochemical signals to pass between neurons. These synapses have weights, which, in combination with the inputs, determine which neurons in the subsequent layer are activated, which in turn affect which neurons in the next layer are activated, and so on. The final layer of neurons feeds their results to the outputs, and whichever output is strongest, the classification most associated with the input, for example, is the algorithm's prediction. The operation of the hidden layers can be particularly mysterious to the untrained eye, and, as explained below, even experts can't develop meaningful interpretations of their output. Synapse weights can initially be assigned randomly, and are then trained through a technique known as backpropagation. The MLPNN is fed data for which the correct result is known. For instance, the image of a tiger and the classification tiger. If the MLPNN misclassified the image, the weight of the synapses that would have led to a tiger classification are slightly increased, while the weight of the synapses that led to other classifications are slightly decreased. With enough training data, the synapse weights eventually converge to their optimal values, and ideally, the MLPNN now classifies tiger images with a high level of accuracy. While unarguably the most complex machine learning algorithm discussed here, neural networks are also the most exciting and active area of machine learning research today. With the massive increases in datasets and computational power now available today, which features neural networks with many layers, can be applied to many complex datasets like audio and images. There is no dearth of applications for neural networks, and some of the biggest players in the industry are applying them towards cutting-edge solutions. Amazon uses neural networks to generate product recommendations. Massachusetts General Hospital uses deep learning to improve patient diagnosis and treatments. Facebook uses deep neural networks for facial recognition, and Google powers Google Translate with neural networks. Pros: highly scalable. With massive datasets, other algorithms can eventually plateau in performance. See this image from this slideshow presented by Dr. Andrew Ng, chief scientist at Baidu. While neural network performance can keep improving. An online method. Neural networks can be incrementally trained with new data. Space efficient. Like Bayesian classifiers, they are represented by a list of numbers. For Bayesian classifiers, this list represents feature probabilities. For neural networks, they represent synapse weights. Cons. Black box method. In large neural networks with many thousands of nodes and an order of magnitude more synapses, it's difficult, if not impossible, to understand how the algorithm determined its output. The sheer level of complexity of neural networks, as demonstrated even in this highly simplified explanation of them, means that highly skilled AI researchers and practitioners are needed to properly implement them. Support vector machines. Support vector machines, what are they? A support vector machine, or SVM, is a supervised machine learning algorithm that can be employed for both classification and regression purposes. SVMs are more commonly used in classification problems, and as such, this is what we will focus on in this post. SVMs are based on the idea of finding a hyperplane that best divides a dataset into two classes, as shown in the image below. Support vectors. Support vectors are the data points nearest to the hyperplane, the points of a dataset that, if removed, would alter the position of the dividing hyperplane. Because of this, they can be considered the critical elements of a data set. What is a hyperplane? As a simple example, for a classification task with only two features, like the image above, you can think of a hyperplane as a line that linearly separates and classifies a set of data. Intuitively, the further from the hyperplane our data points lie, the more confident we are that they have been correctly classified. We therefore want our data points to be as far away from the hyperplane as possible while still being on the correct side of it. So when new testing data is added, whatever side of the hyperplane it lands will decide the class that we assign it to. How do we find the right hyperplane? Or, in other words, how do we best segregate the two classes within the data? The distance between the hyperplane and the nearest data point from either set is known as the margin. The goal is to choose a hyperplane with the greatest possible margin between the hyperplane and any point within the training set, giving a greater chance of new data being classified correctly. But what happens when there is no clear hyperplane? This is where it can get tricky. Data is rarely ever as clean as our simple example. A dataset will often look more like jumbled balls, which represent a linearly non-separable dataset. In order to classify a dataset like the one above, it's necessary to move away from a 2D view of the data to a 3D view. Explaining this is easiest with another simplified example. Imagine that our two sets of colored balls are sitting on a sheet, and the sheet is lifted suddenly, launching the balls into the air. While the balls are up in the air, you can use the sheet to separate them. This lifting of the balls represents the mapping of data into a higher dimension. Because we are now in 3 dimensions, our hyperplane can no longer be a line. It must now be a plane as showed in the example below. The idea is that the data will continue to be mapped into higher and higher dimensions, while a hyperplane can be formed to segregate it. Pros and cons of support vector machines. Pros. Accuracy. Works well on smaller, cleaner datasets. It can be more efficient because it uses a subset of training points. Isn't suited to larger datasets as the training time with SVMs can be high. Less effective on noisier datasets with overlapping classes. SVM uses. SVM is used for text classification tasks such as category assignment, detecting spam, and sentiment analysis. It is also commonly used for image recognition challenges, performing particularly well in aspect-based recognition and color-based classification. SVM also plays a vital role in many areas of handwritten digit recognition, such as postal automation services. There you have it, a very high-level introduction to support vector machines. Support vector machines. Support vector machines, or SVMs, are a complex but powerful classification technique. Working on numerical data, SVMs classify by finding the dividing line, formerly called a maximum margin hyperplane, that separates data most cleanly. This is not always inherently obvious, so sometimes polynomial transformation, transforming the data onto different axes, for example, instead of plotting GPA versus SAT score for predicting if a student is admitted to a certain university, you may transform the data by plotting GPA squared versus SAT score squared. Is used to transform data to a different space, where the dividing line will be more clear. Classification is based on which side of the dividing line new data falls. This can get very complex even for technical people, though once the SVM is constructed, it's fairly simple to use. While most commonly used for classification problems, SVMs have been extended to regression tasks in more recent years. Example: SVMs are often used with very complex data for applications such as recognizing handwriting, facial expression classification, and classifying images. For example, an SVM could recognize numerals written in the Arabic or Persian script with a 94% accuracy. In this case, there were 10 classes, 0, 1, 2, 3 through 9, and the SVM operated on a digit-by-digit case to classify each handwritten digit into one of those classes. In this case, the SVM was more accurate than a neural network. The complexity of choosing the features, in this case, another algorithm was used for feature extraction, which involved the proportion of white pixels in each image of a handwritten digit, makes this sort of problem more suitable for an SVM than, say, a Bayesian classifier, where features are typically well identified beforehand. Pros: very fast at classifying new data. There is no need to go through training data for new classifications. Can work for a mixture of categorical and numerical data. SVMs are robust to high dimensionality, meaning they can work well even with a large number of features, and they're highly accurate. Cons: black box technique. Unlike Bayesian classifiers and decision trees, SVMs don't offer easily digestible data under the hood. An SVM may be a highly effective classifier, but you may not be able to figure out why it makes some of those classifications. Typically requires a very large dataset. Other methods, like decision trees, can still give interesting output for small datasets. This may not be the case with an SVM. SVMs are not online. They will need to be updated every time new training data is to be incorporated. What's the difference between a CPU and a GPU? Key difference: a CPU carries out all the arithmetic and computing functions of a computer. A GPU is an electronic circuit unit that is designed to rapidly manipulate and alter memory to increase the rate at which the system builds images in a frame. CPUs and GPUs are often used when referring to computers and its technologies. Though these words are used daily, people are often confused as to what technology performs what jobs. When a normal person opens a computer, he is often baffled with the amount of chips, wires, and clips that are visible inside the system. Unless he is well versed with the computing technology, he would not be able to distinguish anything from the other. This is one of the main reasons why computer technicians are able to charge such high and mighty charges for even taking a look at the system. Hence, it is important to keep a little knowledge about which technology offers which purpose. A central processing unit, or CPU, is the hardware within a computer system that carries out the instructions of a computer program by performing the basic arithmetical, logical, and input-output operations of the system. It is also called a central processor unit, or more commonly, a processor. However, many mistakenly use the term CPU to refer to the housing unit that stores all of the computer's hardware, whereas in actuality, it is just the small processor chip that runs the computer's programs. In large computers, the CPU requires one or more printed circuit boards. However, in personal computers and small workstations, the ones most of us use, the CPU is housed in a single silicon chip called a microprocessor. The fundamental function of a CPU is to run or execute a program. A program is essentially a sequence of stored instructions, which is represented by a series of numbers that are kept in some kind of computer memory. CPUs follow a four-step process in their operation: fetch, decode, execute, and write back. In addition to executing a program, the CPU is also responsible for keeping an eye over system functions, for executing scripts, and for executing complex calculations, which are often used in software rendering. CPUs also initiate transfer of large blocks of data, as well as read or write data to and from peripheral devices, such as CDs, DVD, USB drives, etc. Since the CPU is responsible for practically all the processes running in the computer, it is only acceptable to state that the faster the CPU is, the faster the applications can run. However, a very large CPU is also not necessary for most home computers, as many of us do not run that many programs at a single time. There are two typical components of a CPU: arithmetic logic unit, or ALU, and the control unit, CU. The ALU performs arithmetic and logical operations, while the CU extracts instructions from memory and decodes and executes them, calling on the ALU for help when necessary. The graphics processing unit, GPU, is an electronic circuit unit that is designed to rapidly manipulate and alter memory to increase the rate at which the system builds images in a frame. Its main purpose is to quicken the image building process that is intended for output to a display. The modern GPUs are very efficient in manipulating computer graphics, and its highly parallel structure makes it more effective than general CPUs for processing large blocks of data that are done in parallel. GPUs are more effective when it comes to manipulating computer graphics, especially when they are done in parallel. The GPUs can be placed on the motherboard closer to the CPU, or they can be found on their own silicon chip. The term GPU was designed by NVIDIA in 1999 for their GeForce 256. Wikipedia states that the product was marketed as the world's first GPU, or graphics processing unit, a single-chip processor with integrated transform, lighting, triangle setup and clipping, and rendering engines that are capable of processing a minimum of 10 million polygons per second. NVIDIA's competitor, ATI Technologies, tried to unsuccessfully coin and popularize the term VPU, or Visual Processing Unit. Initially, the CPUs are responsible for handling all of the computing and instructions that it receives from the user and the system. However, with the increase of technology and the demand of technology, it was best to take some of the pressure of the CPU and give it to other processors. In comparison to CPUs, GPUs have more transistors that can handle more work and offers greater resolution. Most of the GPU's transistors perform calculations related to 3D technologies. They were originally used to accelerate the memory-intensive work of texture mapping and rendering polygons. Many GPUs also support technologies for advanced gaming or digital playback, offering better and advanced systems. The concept of dynamic and static programming. When a code is generated, then the nature of code is a very important factor in itself. A company which gets an application developer has to keep in focus the points relating to the time span after which the code has to be updated. If a code has to be updated after a short time span, then the concept of dynamic programming comes into being. When the code has to be developed after a long time span, then the nature of code is expected to be static. The concept of static code is difficult to manage as a constant team of developers is constantly required so that piece of code can be rearranged whenever it is required. Hence, it may also happen that the code nature is left undecided, while the type is kept such that it can be changed according to the requirements. When a code is made, it is made such that there are no compatibility issues related to the code. When a company decides to execute the code, then it should not have complications related to the process of execution. When a process is executed, then it may happen that the process gets stuck in between, and the execution cycle gets a halt. This can be very damaging for the code as it cannot be reverted to the requirement analysis phase. Therefore, all the requirements have to be kept in mind prior to the final execution of the program, including the business logo, which is one of the main ingredients of the company reputation structure. Enter into the programming world with Python training. The engineering curriculum in India suggests that colleges start programming classes for students with C, followed by C++ and Java. This has created the assumption that C kickstarts the coding lessons for freshmen. A simple metaphor would help you understand the difference between starting programming lessons with C and Python better. To learn programming with C or C++ is like trying to learn to drive by manufacturing, assembling, and then using a car. You will eventually learn to drive, but at the cost of unnecessary pressure and information a little too soon than required. However, if one starts with Python training, it would be like learning to drive automatic. So, you need not know how the engine works, how to assemble it, what your car can or cannot do, etc. The only thing you get to do originally is what you ought to do, in other words, programming. Later comes the technical aspects. Python can be used to process anything that can be saved on a computer, like numbers, text, data, statistics, etc. Its easy-to-use features will keep programmers engaged and excited as they begin to learn Python. It has become famous with its characteristics like easy indentation, naming conventions, modularity, etc. Python is widely used in daily applications of Google, NASA, the New York Stock Exchange, and our favorite video sharing website, YouTube. Not just in the industry big shots, Python is extensively used even in business, government, and non-government organizations too. Python is called an interpreted language. This means the code written in Python is converted to computer-readable code at the program runtime. Initially, Python was called a scripting language, suggesting its only use in trivial jobs. But as time advanced, its user-friendly features started making it the most commonly used language for writing large programs. The 4 features that created such high demand for Python are: high-level language. Python is a high-level language. It means that it provides a level of abstraction that helps you focus on algorithms and the functionality of the code. You need not worry about the low-level details like memory management, etc. Also, there is a huge library of pre-coded functionalities for almost any need. Dynamic. The main aspect that makes Python a friendly language is its runtime. Features like dynamic typing, easy introspection, and reflection all make coding easier and reduces the time of programming. Expressive syntax. Expressive syntax includes how easy it is to express an idea and how concisely you can do it. Python training allows you to write complex code within few lines while keeping its readability intact. Readability. It is the key strength of Python. Instead of curly braces, indentation helps in easy readability and understandability of the program. Well-indented code delimits the blocks of code in a program. It is very important for writing or understanding code. Thus, with the above features, Python training can very well act as a mentoring course to freshmen. It allows them to focus on problem decomposition and data type design rather than dealing with trivial implementation issues. The concept like procedures, loops, or user-defined objects can be instilled in their brains in the very first course. It can be stated as a bottom line that Python is a freshman-friendly yet powerful language that lets the beginners focus on algorithms, abstracting away low-level implementation details, making it the best first programming language. Deep Learning, Machine Learning and Data Analytics Explained. Written by David Feldspar. Narrated by Jason R. Gray. Introduction. Deep learning is a new area of machine learning research, which has been introduced with the objective of moving machine learning closer to one of its original goals, artificial intelligence. Deep learning is not only a massive buzzword spanning business and technology, but also a concept that will transform most industries and jobs, as well as the way we live our lives. Data mining and analytics have played an important role in knowledge discovery and decision-making and supports in the process industry over the last several decades. As a computational engine to data mining and analytics, machine learning serves as a basic tool for information extraction, data pattern recognition, and predictions. From the perspective of machine learning, this paper provides a review on existing data mining and analytics applications in the process industry over the past several decades. The state-of-the-art of data mining and analytics are reviewed through 8 unsupervised learning and 10 supervised learning algorithms, as well as the application status of semi-supervised learning algorithms. Several perspectives are highlighted and discussed for future researches on data mining and analytics in the process industry. In recent years, many unions or countries have announced a new round of development plans in manufacturing. For example, the European Union proposed 20-20-20 goals to achieve a sustainable future, which means 20% increase in energy efficiency, 20% reduction of CO2 emissions, and 20% renewables by 2020. Those goals can only be realized by incorporating more intelligence into industrial manufacturing process. The U.S. government has proposed a new industrial internet framework for developing the next generation of manufacturing. Japan announced a revitalization plan for manufacturing. Germany proposed the concept of Industry 4.0, the main aim of which is to develop smart factories for producing smart products. Similarly, China has announced a new manufacturing plan more recently, which is known as China Manufacturing 2025, the aim of which is to also make the manufacturing process more intelligent. As an important part of manufacturing, the process industry needs to be reformulized in the era of new information technologies. How to improve process understanding and accumulate effective knowledge plays an important role in all aspects of the process industry, such as sustainability design, system integration, advanced process and quality control, decision supports, etc. From the viewpoint of automation, Data mining and analytics may serve as a basic tool to promote the process industry from machine automation to information automation, and then to knowledge automation. In the past several decades, a large amount of data has been achieved in the process industry due to the wide use of distributed control systems. While it becomes more and more difficult to build first-principle models in those increasingly complex processes, data-driven process modeling, monitoring, prediction, and control have received much attention in recent years. At the very beginning, those large amounts of data have rarely been used for detailed analysis, which are instead only used for routinely technical checks and process log fulfillments. Later, awareness of the importance in extracting information from data has taken a leading role in the process industry. At the same time, the technical development of database and data analysis has been in a fast pace during those years. Therefore, research on data mining and analytics in the process industry has become quite popular since then. By analyzing the patterns of process data and relationships among variables, useful information can be extracted, based on which statistical models can then be developed for various applications, such as process monitoring, fault diagnosis, mode clustering, soft sensing of key variables and quality variables, etc. In a word, the main aim of data mining and data analysis is to extract useful information from process data and transfer it to effective knowledge for improvement of understanding and decision supports of the process. To effectively carry out data mining and analytics in the process industry, machine learning algorithms have always played an important role. There are 4 different types of machine learning algorithms, termed unsupervised learning, supervised learning, semi-supervised learning, and reinforcement learning. While reinforcement learning is used in robotics, gaming, and navigation areas, other 3 types of machine learning have all been widely used for data mining and analytics in the process industry. According to the introduction provided by Wikipedia, machine learning is a subfield of computer science that evolved from the study of pattern recognition and computational learning theory in artificial intelligence. However, the theory of probability and statistics also plays a very important role in modern machine learning. Machine learning explores the study and construction of algorithms that can learn from and make predictions on data. In 1959, Arthur Samuel defined machine learning as a field of study that gives computers the ability to learn without being explicitly programmed. And later, Tom M. Mitchell provided a widely quoted, more formal definition. A computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T as measured by P improves with experience E. Compared to other definitions, this definition is more notable. Since its definition, machine lots of attention in various areas, such as pattern recognition, industrial applications, bioinformatics, image analysis, etc. Although the research of machine learning sunk for several times, the ship has been resailed and will become increasingly more powerful since we entered the 21st century. During the last several decades, machine learning has been playing an important role in constructing experience-based models from process data, based on which useful information can be extracted. New patterns of data can be identified, predictors can be made more easily for new data samples, decisions can be made more quickly and effectively, etc. All these applications of machine learning have fundamentally changed the manufacturing style of the process industry. For data mining and analytics in the process industry, lots of work has been reported in the past years. Among them are several reviews and books which have provided more detailed state-of-the-art of the research on this topic. However, there exists no such report that details data mining and analytics from the viewpoint of machine learning, although the terminology has been mentioned many times in various papers and books. The first aim of this paper is to provide a systematic review on data mining and analytics in the processing industry up to date from the viewpoint of machine learning. This will include reviews of topics of unsupervised learning, supervised learning, and semi-supervised learning methods for applications in the process industry. Under each specific review topic, various applications of machine learning algorithms will be introduced, with detailed discussions among different methods. The second aim of this paper is to provide new perspectives for future application of machine learning algorithms in the process industry. With the rapid development of the modern industry, new phenomena of process data have emerged, for example, the big data problem, which need to be carefully addressed when applying machine learning methods. On the other hand, the technology of machine learning itself continues to evolve all the time. For example, neural networks have been used for data mining for many years. With the increased computing power, we can create neural networks with many layers, which is known as deep learning neural networks. Both the change in industry environments and the increased power of modern technologies have made the application of machine learning more challenging, more exciting, and thus need more future investigation and more ambitious researchers to explore in this area. 10 ways predictive analytics can help the banking sector. Here are the 10 ways in which predictive analytics is helping the banking sector. 1. Fraud detection. Fraud is becoming an area of big concern for every sector, and for banking and financial firms, it can cost a lot to them. For individuals, it's even more dangerous because they are at risk of losing their identity in the first place. Digitization has paved the way for cybercriminals to commit more frauds. Thus, banks need intelligent systems and tools to deal with them. Predictive analytics, machine learning, big data, data mining, and stream computing are a few of the tools that are helping to catch these frauds. Analytics can be used to recognize frauds that are not very obvious, and then predictive analytics can be implemented on them to analyze them further. Data integration, utilizing unstructured data and machine learning techniques like supervised and unsupervised learning, can help detect fraud cases by following a pattern. 2. Application screening. Predictive analysis in banking can help process huge volumes of applications without excluding important variables, without delays or errors, without growing tired, all of it with regularity and steadiness. The results are very much accurate and authentic to be used, so ultimately, there doesn't have to be a comparison between traditional or manual screening and analytics. 3. Customer acquisition and retention. Predictive analytics help in the process for optimized targeting, making it easier for banks to instantly identify the high-value customer segments most likely to respond. The customer base can further expand by acquiring the right type of customer. Based on a report, it was seen that the banks that adopted predictive analytics had an increase of about 10% in new customer opportunities over a year. Also, predictive analytics helps banks and financial institutions retain their customers. It identifies the customers most likely to defect before they end their relationship. It keeps the right customers longer, and it predicts which actions will earn their loyalty. Applying this technology would also help discover the churn patterns and develop profiles of users who have left, to get an insight of why they left and discover strategies to keep them satisfied. Customer retention is another area where banks need to focus more today in order to reduce customer sapping. Loyal customers need to be rewarded, and customer attrition needs to be minimized. Sometimes it gets too late to retain a customer because they tend to have a large customer base and, hence, lose track of them. It's easy to look out for a new customer, but the old ones are always valuable. Predictive analysis helps identify which customers are willing to switch to any other bank and the reason behind their decision. It examines customer service performance, spending, past service, and other behavior patterns to predict the likelihood of a customer wanting to stop its services anytime in the near future. 4. Knowing customer buying habits. Targeting the right product and tracking customer usage is a challenge before banks, which they independently and in conjunction with retailers are trying to curb. With predictive analytics, banks can rapidly segregate various customer segments and replace it with highly relevant, individualized messages tailored to each customer's profile, resulting in a higher response rate. This ultimately helps deliver the right product to the right person. As in, if someone who has a history of buying gadgets, then the sale of high-end gadgets could be targeted at him, and in fact he would be happy to get such updates. 5. Cross-selling. Efficient cross-selling of products can happen by analyzing the existing customer behavior at places where multiple products are offered. Which specific products are to be sold to whom, hence predicting the outcome, is what successful cross-sellers do. And all of this results in more effective cross-selling, thus increasing profitability and strengthening the customer relationship. Today, securing one profitable customer is a big task for banks. Hence, cross-selling another product to an existing customer helps a lot. Predictive analytics helps examine customers' usage, spending, and other behavior, and leads to effective cross-selling of the right product at the right time. 6. Collections. Banks have a mix of customers who always pay on time and those who lag. It is a tricky task to keep track and maintain records of all individuals and differentiate who to focus on more. Predictive analytics offers clear benefits in this area. Banks can obtain a better understanding of their portfolio risk and thus improve the productiveness of the collections process. Most importantly, analytics helps identify the customers who would be at risk in the future and what actions banks should take to achieve positive results. 7. Better cash and liquidity planning. Predictive analytics can help banks track the past usage patterns and the daily coordination between the in and out payments of their branches and ATMs, hence predicting the future needs of their potential customers. Optimal management of liquid assets can result in their extra income, and a proper analytics plan can help obtain an overview of future changes in investment and liquidity options. 8. Marketing optimization. Predictive analytics helps marketers to plan marketing campaigns and programs and monitor the results closely. By providing an insight into customer behavior and attitudes and a complete current view of your customers, analytics help your marketing team deliver the right message at the right time to the right customers. 9. Customer lifetime value. Customers' lifetime value is how long the organizations are able to retain their customers. Identifying who the best customers are, making them better in different ways, and once you win them over, securing their loyalty, are a few areas that banks are focusing on. Predictive analytics helps know which customers should be the focus of new customer engagement efforts, identify the previous factors that enhanced returns on customer engagements in the past, and use that knowledge to understand why customers responded to certain messages and promotions. 10. Feedback management. Feedback management is really important. Predictive analytics allows banks and financial firms to keep up their relationship with the customers by giving them the right services and products for their need, and matching individual preferences in the most sorted way. Applications for machine learning in finance. Let's now look at how machine learning is impacting elements of the financial sector. Fraud prevention. Financial service providers have no greater responsibility than protecting their clients against fraudulent activity. Financial fraud costs Americans alone $50 billion annually. Old ways of keeping clients' accounts secure are no longer good enough. With each advancement in data security, criminals have stepped up to the challenge. To protect clients' data from increasingly sophisticated threats, institutions and companies must stay one step ahead of the hackers. Machine learning enables applications to thwart security breaches by outthinking the criminals. By comparing each transaction against account history, machine learning algorithms are able to assess the likelihood of transactions being fraudulent. Unusual activities, such as out-of-state purchases or large cash withdrawals, raise flags that can cause the system to introduce steps to delay the transaction until a human can make a decision. In many cases, depending on the nature of the attempted transaction, a purchase or withdrawal attempt may be automatically declined by the system. Unlike a human agent, the algorithm is able to quickly weigh the transaction details against thousands of data points and make a determination whether or not the attempted activity is uncharacteristic of the account owner. And unlike non-AI software, machine learning programs learn from each action the account owner takes, and from each decision the software makes. Over time, the algorithms adjust themselves in response to changing habits on the part of the account owner. In order for machine learning to be effective, it must be able to quickly access and digest large amounts of data. Realizing the value of machine learning, Amazon, Microsoft, IBM, and Google are each integrating machine learning capabilities into their cloud-based developer interfaces. As criminals become more advanced in their strategies, only computer systems with access to big data and with the ability to think and learn will be able to stop them. Risk management. It should come as no surprise that machine learning technology can be a powerful ally in the quest for better risk management. While traditional software applications predict creditworthiness based on static information from loan applications and financial reports, machine learning technology can go further and also analyze the applicant's financial status as it may be modified by current market trends and even relevant news items. By applying predictive analysis to huge amounts of data in real time, machine learning technology can detect rogue investors working in unison across multiple accounts, something that would nearly be impossible for a human investment manager. Efficiency is another benefit of machine learning. By assuming a substantial amount of the burden to monitor accounts, machine learning systems enable investment managers to focus on more productive tasks, such as servicing clients. Investment predictions. Computer-aided trading services have been around for some time. They allow investors to have an order placed when a stock reaches a predetermined price, and to sell when that price drops below a certain limit. By automating functions, such platforms make trading easier for large and small investors alike. While they can even make recommendations based on automated analysis of market trends, they have limitations. In recent years, hedge funds have increasingly moved away from traditional predictive analysis methods and have adopted machine learning algorithms for predicting fund trends. Using machine learning, fund managers hope to identify market changes earlier than is possible with traditional investment models. The potential of machine learning technology to disrupt the investment banking industry is being taken seriously by major institutions. J.P. Morgan, Bank of America, and Morgan Stanley are developing automated investment advisors powered by machine learning technology. Wise fintech companies will likely follow suit. Customer service. Poor customer service remains one of the chief complaints among consumers, regardless of the industry. Originally, the complaint centered on slow customer service, but with the universal utilization of automated phone support, customers are frustrated by not being able to talk to a human. For the innovative financial service company willing to invest in machine learning technology, this should not represent a problem, so much as an opportunity. The advantages of automated customer support systems include directing the customer to the correct department, giving them the option to resolve minor problems using the automated interface, and keeping the customer from having to wait for someone to answer the phone, all without human interaction. The company benefits by not paying salaries to personnel who would handle these tasks, and the customer supposedly benefits by having their problems handled with the expeditiousness of modern computers. In theory, anyway. In reality, many customers do not benefit from automated customer service when their problem is uncommon and not represented by a numeric option. While definitely an improvement, voice recognition often still fails to accommodate the unusual request, with, quote, "I'm sorry I'm not understanding you, please hold for assistance," unquote, being the stock response to a customer with a unique problem. The solution, as provided by machine learning technology, is not to replace automated customer support systems, but to make them better. The tremendous power of machine learning technology to access data, recognize patterns, and interpret behavior means that the technology can be used to create automated customer support systems that mimic a human agent, with the ability to understand and respond to uncommon concerns. By making phone and online customer support portals more human-like, financial institutions can provide efficient support that reduces customer blowback. Additionally, machine learning technology can help customers make better product selections by weighing previous account activities against current data provided by the client and from elsewhere. Product or service recommendations can be made directly to the client or through a financial advisor. The result is a better informed client whose time is not wasted by inappropriate offerings. One of the most important paybacks for companies that invest in machine learning customer service is the ability to better understand the needs of each individual customer, which is always a good thing. No company, fintech or fish market, operates without sound management. And for management to be sound, it must function effectively and efficiently. Machine learning technology, perhaps surprisingly, can help executives and managers to perform their jobs with greater ease than ever before. We are talking about digital assistants, and the competition to develop a winning platform is fierce. Google, Apple, Facebook, and Microsoft all have their own version of the virtual secretary. Google's Allo, Apple's popular Siri, Facebook's M, and Microsoft's Cortana currently represent the state-of-the-art in digital helpers. Each targets a certain market, and each has its own advantages and limitations. For the innovative fintech startup intent on making its own toys, it is a good time to consider the competition and then take away what will work best in the business office of a financial institution. Machine learning technology includes several functionalities that can be useful for developing a custom digital assistant, namely speech recognition, access to big data, powerful data analytics capabilities, the ability to integrate with social media, email, and third-party applications and platforms, and pattern and behavior recognition. Although this list is far from inclusive, it is easy to see how machine learning technology can replace certain executive duties while augmenting others. Whether a financial service company chooses to invest in the development of a virtual assistant platform for its own operation, or for the purpose of offering the platform as part of a service package for their clients, the return on investment is likely to be substantial. Marketing. Having read of the many ways in which machine learning can help keep accounts secure, improve risk management, and offer investment strategies, you might not expect the technology to also be a good marketing tool. On the contrary, the ability to make predictions based on past behaviors is fundamental to any successful marketing effort. By analyzing web activity, mobile app usage, and response to previous campaigns, Machine learning software can predict the effectiveness of a marketing strategy for a given customer. With the online marketing power of Google now augmented by machine learning, it is possible for developers working in the financial sector to create smart tools that make the job of marketing executives easier than ever. The potential of machine learning to supercharge the marketing industry has led to a spurt in machine learning-based advertising startups in the last year. So many, in fact, that 2015 saw no less than 10 acquisitions in this space, including the Twitter acquisition of Telepart for more than $530 million. Clearly, big money has its eye on machine learning as the next big thing in marketing. Network security. Among the top considerations for any network administrator or data security professional is how to recognize suspicious patterns occurring across their networks. The challenge to identify such patterns lends itself perfectly to the capabilities of machine learning. The power of intelligent pattern analysis, combined with big data capabilities, certainly gives machine learning technology an edge over traditional non-AI tools. One might go so far as to declare machine learning as the last hope of securing critical networks against professional and state-sponsored cyber attacks. Despite costly and increasingly complex IT security platforms against modern cyber attacks, so far, hackers have breached the network security of such mammoths as the U.S. Department of Justice, the U.S. Democratic National Committee, or DNC, the Internal Revenue Service, Snapchat, LinkedIn, and Oracle. Clearly, organizations need to rethink their approach to cybersecurity. Existing systems do not necessarily need to be abandoned, but the additional layer of wizardry which machine learning security can provide is the next step in the evolution of network security. Adding credence to the notion that machine learning is a viable network security tool, Microsoft is investing heavily in its own deterministic machine learning big data platform. Using statistical analysis of baseline metrics along with historical data from bad behaviors, computer scientists are constructing models that can identify anomalous or abnormal behaviors. While not every organization replicates the resources of IBM, the lessons learned from the tech giant will help fuel independent development in the fintech, financial, IT security space. How Ignite can help. To foresee all the ways in which machine learning will impact the financial sector would require the highly sought-after and yet unperfected technology, the crystal ball. For the lack of it, we can only envision how the technology can be used to solve problems now and in the near future. The 7 applications we have discussed surely represent a technology in its infancy. No doubt, innovative fintech startups are already adding to the list. As a financial service provider, finding fresh, innovative ways of serving your clients and customers is key to your longevity, and knowing how to access and use big data is only the start. Today's landscape demands that you do more. You must bridge new technology with systems that are familiar to your users, while improving the level of service minute by minute. That's where Ignite outsourcing comes in. Deep learning in data mining and machine learning. The main concept in deep learning algorithms is automating the extraction of representations, or abstractions, from the data. Deep learning algorithms use a huge amount of unsupervised data to automatically extract complex representations. These algorithms are largely motivated by the field of artificial intelligence, which has the general goal of emulating the human brain's ability to observe, analyze, learn, and make decisions, especially for extremely complex problems. Work pertaining to these complex challenges has been a key motivation behind deep learning algorithms, which strive to emulate the hierarchical learning approach of the human brain. Models based on shallow learning architectures such as decision trees, support vector machines, and case-based reasoning, may fall short when it's useful information from complex structures and relationships in the input corpus. In contrast, deep learning architecture's ability to generalize in non-local and global ways, generating learning patterns and relationships beyond immediate neighbors in the data. Deep learning is, in fact, an important step towards artificial intelligence. It not only provides complex representations of data, which are suitable for AI tasks, but also makes the machines independent of human knowledge, which is the ultimate goal of AI. It extracts representations directly from unsupervised data, without human interference. A key concept underlying deep learning methods is distributed representations of the data, in which a large number of possible configurations of the abstract features of the input data are feasible, allowing for a compact representation of each sample, and leading to a richer generalization. The number of possible configurations is exponentially related to the number of extracted abstract features. Noting that the observed data was generated through interactions of several known or unknown factors, and thus, when a data pattern is obtained through some configurations of learned factors, additional unseen data patterns can likely be described through new configurations of the learned factors. Compared to learning based on local generalizations, the number of patterns that can be obtained using a distributed representation scales quickly with the number of learned factors. Deep learning algorithms lead to abstract representations because more abstract representations are often constructed based on less abstract ones. An important advantage of more abstract representations is that they can be invariant to the local changes in the input data. Learning such invariant features is an ongoing major goal in pattern recognition. For example, learning features that are invariant to the face orientation in a facial recognition task. Beyond being invariant, such representations can also disentangle the factors of variations in the data. The real data used in AI-related tasks mostly arises from a complicated interaction of many sources. For example, an image is composed of different sources of variations, such as light, object shapes, and object materials. The abstract representations provided by deep learning algorithms can separate the different sources of variations in the data. Deep learning algorithms are actually deep architectures of consecutive layers. Each layer applies a nonlinear transformation on its input and provides a representation in its output. The objective is to learn a complicated and abstract representation of the data in a hierarchical manner, bypassing the data through multiple transformation layers. The sensory data, for example pixels in an image, is fed to the first layer. Consequently, the output of each layer is provided as input to its next layer. Stacking up the nonlinear transformation layers is the basic idea in deep learning algorithms. The more layers the data goes through in the deep architecture, the more complicated the nonlinear transformations which are constructed. These transformations represent the data, so deep learning can be considered as a special case of representation learning algorithms, which learn representations of the data in a deep architecture with multiple layers of representations. The achieved final representation is a highly nonlinear function of the input data. It is important to note that the transformations in the layer of deep architecture are nonlinear transformations which try to extract underlying explanatory factors in the data. One cannot use a linear transformation like PCA as the transformation algorithms in the layer of deep structure, because the compositions of linear transformations yield another linear transformation. Therefore, there would be no point in having a deep architecture. For example, by providing some facial images to the deep learning algorithm, at the first layer it can learn the edges in different orientations. In the second layer, it composes those edges to learn more complex features, like different parts of a face, such as lips, noses, and eyes. In the third layer, it composes those features to learn even more complex features, like face shapes of different persons. These final representations can be used as the feature in applications of facial recognition. This example is provided to simply explain, in an understandable way, how a deep learning algorithm finds more abstract and complicated representations of data by composing representations acquired in a hierarchical architecture. However, it must be considered that deep learning algorithms do not necessarily attempt to construct a predefined sequence of representations at each layer, such as edges, eyes, faces, but instead more generally perform nonlinear transformations in the different layers. These transformations tend to disentangle factors of variations in data. Translating this concept to more appropriate training criteria is still one of the main open questions in deep learning algorithms. The final representation of data constructed by the deep learning algorithm, or output of the final layer, provides useful information from the data, which can be used as features in building classifiers, or even can be used for data indexing and other applications which are more efficient when using abstract representations of data rather than high-dimensional sensory data. Learning the parameters in deep architecture is a difficult optimization task, such as learning the parameters in neural networks with many hidden layers. In 2006, Hinton proposed learning deep architectures in an unsupervised, greedy, layer-wise learning manner. At the beginning, the sensory data is fed as learning data to the first layer. The first layer is then trained based on this data, and the output of the first layer, the first level of learned representations, is provided as learning data to the second layer. Such iteration is done until the desired number of layers is obtained. At this point, the deep network is trained. The representations learned on the last layer can be used for different tasks. If the task is a classification task, usually another supervised layer is put on top of the last layer, and its parameters are learned, either randomly or by using supervised data and keeping the rest of the network fixed. At the end, the whole network is fine-tuned by providing supervised data to it. Here, we explain two fundamental building blocks: unsupervised single-layer learning algorithms, which are used to construct deeper models, autoencoders, and restricted Boltzmann machines, RBMs. These are often employed in tandem to construct stacked autoencoders and deep belief networks, which are constructed by stacking up autoencoders and restricted Boltzmann machines, respectively. Autoencoders, also called autoassociators, are networks constructed of three layers: input, hidden, and output. Autoencoders try to learn some representations of the input in the hidden layer in a way that makes it possible to reconstruct the input in the output layer based on these intermediate representations. Thus, the target output is the input itself. A basic autoencoder learns its parameters by minimizing the reconstruction error. This minimization is usually done by stochastic gradient descent, much like what is done in multilayer perception. If the hidden layer is linear, and the mean squared error is used as the reconstruction criteria, then the autoencoder will learn the first k principal components of the data. Alternative strategies are proposed to make autoencoders nonlinear, which are appropriate to build deep networks as well as to extract meaningful representations of data, rather than performing just as a dimensional reduction method. Bengio et al. Have called these methods regularized autoencoders, and we refer an interested reader to that paper for more details on algorithms. Another unsupervised single-layer learning algorithm, which is used as a building block in constructing deep belief networks, is restricted Boltzmann machine, RBM. RBMs are likely the most popular version of Boltzmann machine. They contain one visible layer and one hidden layer. The restriction is that there is no interaction between the units of the same layer, and the connections are solely between units from different layers. The contrastive divergence algorithm has mostly been used to train the Boltzmann machine. 5 steps to implementing unsupervised big data machine learning. There is quite a buzz around unsupervised machine learning for asset maintenance. For good reason. Unsupervised machine learning provides the benefits of the digital twin, or real-time alerts to emerging asset degradation and failure based on analysis of sensor data. At the same time, unsupervised machine learning does not come with the hefty price tag, because the advanced AI algorithm can analyze vast amounts of data in the cloud and is sensor agnostic. Big data machine learning, both supervised and unsupervised, are at the forefront of the move to the smart factory. Industrial plants now recognize that only a fraction of their existing SCADA data is ever used for condition-based monitoring. Furthermore, because controls are manually set, only breaches of control limits are monitored. The result is that the emerging failures are typically ignored until it is too late and the CBM control limits have been exceeded. Unsupervised big data machine learning for asset maintenance. There are 5 discrete steps required for using unsupervised machine learning for asset maintenance. Sensor data generated and stored. Raw sensor data is generated and transmitted to the historian database. Data streamed to the Procesno cloud. All raw sensor data is continuously streamed from the local historian database to the Procesno cloud, whereas condition-based monitoring only monitors a few critical sensors. There are no limits to the number of sensors that can be monitored by Procesno. AI-driven anomaly detection. Whereas CBM tracks breaches of manually set control limits, the Procesno advanced AI algorithm detects anomalies in data patterns. The algorithms are sensor agnostic. They are looking for abnormal data patterns to identify emerging degradations and machine failure. Contextualization of machine behavior. Detecting abnormal sensor data behavior is insufficient. Procesno's algorithm searches for correlations and patterns between sensors, even if they are seemingly unrelated. Once emerging patterns are detected, the facility owner receives an alert of potential failure. Included in an alert is information that provides insights into the failure origin. Which historian databases can be used for unsupervised machine learning? The following is a partial list of the historian databases that can be accessed by the Procesno Unsupervised Machine Learning Cloud. OSI Soft PI Historian, AspenTech Info Plus Historian, Emerson Ovation or Delta V, Schneider Electric Wonderware SITTech Historian, GE Digital, formerly Proficiency, ABB Decathlon, SAP HANA, Siemens Symantec, Honeywell Historian, MS SQL, and Oracle. Comparing supervised versus unsupervised machine learning. There has been much discussion about supervised machine learning, especially given the significant investments in the GE Predix platform and Siemens MindSphere. Supervised machine learning is used by the digital twin. It is called supervised because the algorithm needs access to the data labels of historic downtime records. In the digital twin, a complete and accurate 3D modeling using the asset's blueprints is needed. Once the digital twin is created, the learning algorithm can learn the workings of the machine to be able to duplicate its behavior. Unsupervised machine learning is sensor and asset agnostic. With unsupervised learning, there is no need to understand the physical working of the machine, because the algorithm seeks to detect abnormal data patterns. Because there are few limitations to the amount of sensor data analyzed, an entire factory can be monitored. Ultimately, the differences between supervised and unsupervised model impact price, speed to market, and the number of assets that can be monitored. How machine learning can optimize finance processes. Machine learning is becoming a buzzword in nearly every industry today, and finance is no exception. As its applications and capabilities grow, machine learning is powering finance departments towards the next generation of digitization. Here are 3 ways finance professionals can embed machine learning to boost the maturity of their financial management systems or extend their accounting and reporting capabilities to better meet today's business challenges. Embrace digitization in your finance strategy. Before finance departments can unlock the value of machine learning, they must first ensure that digital tools are at the core of their operations. Machine learning depends on live business and big data being integrated across the organization, which is possible to aggregate in real time only through digital in-memory applications based on a modern ERP platform. With a recent survey showing that nearly 1 in 5 small and mid-sized enterprises today are not using accounting software at all, many businesses are still a step behind in being able to apply more advanced technologies. As new technology makes it easier for finance departments to adopt digital infrastructure that is connected, intelligent, responsive, and predictive, they can also take advantage of machine learning to further improve business performance. Along with digital solutions for managing large amounts of data, machine learning becomes a natural next step to increase efficiency and improve business performance. Use automation where it counts. In today's workplace, finance professionals are spending just 17% of their time on strategic activities, with a lack of automation serving as the culprit for much of this inefficiency. As finance teams move away from managing work through spreadsheets and towards digital and cloud ERP solutions, machine learning can provide an additional edge in driving innovation through the finance function. Digital finance solutions that incorporate machine learning capabilities can greatly expedite transactional tasks and bring teams closer to eliminating manual administrative work entirely. Financial professionals can increase the time spent on strategic priorities by automating back-office processes like procure to pay, order to cash, and record to report. Machine learning programs utilize predictive algorithms to churn through massive amounts of data, working at a much faster speed than traditional processes dependent on human input. Turning non-strategic tasks over to computers will allow corporate finance professionals to spend time on more rewarding and higher value work, like business or deal support or advanced analytics, which will in turn yield increased business opportunities for the entire organization. Supplement human processes with machine support. While not all financial processes can be completely automated, machine learning can help to support transactions and reduce errors in tasks that require human input. For example, it is likely that financial statement auditing will never be completely trusted to machines, as it depends on human judgment in evaluating circumstantial reasoning behind data. However, machines can be useful in using patterns in datasets to highlight potential areas of discrepancy and double-check human work. Machine learning technologies can sort through high volumes of data from financial reports at an exponentially faster pace than humans, and then turn that data over to human eyes, which can subsequently investigate the story behind the numbers and evaluate whether certain patterns or anomalies may be cause for concern. Another process that can allow finance teams to benefit from collaboration between humans and intelligent machines is fraud reduction and cybersecurity. As finance departments are embracing digital solutions for storing and managing financial data, either on-premise or in the cloud, cybersecurity is becoming a top concern for CFOs, who must ensure that access to information is monitored and regulated. Again, machines have the ability to churn through massive sets of data regarding access to and transactions upon those datasets, identifying abnormal patterns or unique access behaviors. Cybersecurity professionals in the enterprise can then analyze the data and determine the next steps that need to be taken to ensure the continual security of financial information, easing the worries of CFOs. By embracing a robust digital strategy, allowing automation to take over administrative work, and applying machine learning to supplement human processes, finance professionals can work at the speed of business today and ensure that their organizations are able to continuously innovate. As the capabilities of machine learning continue to grow, CFOs will need to ensure that their organizations are ready to unlock the full value of automation and machine learning through its many applications in accounting and finance. Thanks again for buying my book. If you have a minute, please leave a review. I take reviews seriously and always look at them. This way, you are helping me provide you better content that you will love in the future. A review doesn't have to be long, just 1 or 2 sentences and a number of stars you find appropriate. Hopefully 5, of course. Also, if I think your review is useful, I will mark it as helpful. This will help you become more known on Amazon as a decent reviewer, and will ensure that more authors will contact you with free ebooks in the future. This is how we can help each other. You can look at these books too: Data Analytics, Data Mining, and Data Science for Business. Disclaimer: the information is provided as is. The author, publishers, and/or marketers of this information disclaim any loss or liability, either directly or indirectly, as a consequence of applying the information presented herein, or in regard to the use and application of said information. No guarantee is given, either expressed or implied, in regard to the merchantability, accuracy, or acceptability of the information. The pages within this ebook have been copyrighted. What are some popular machine learning methods? 2 of the most widely adopted machine learning methods are supervised learning and unsupervised learning. But there are also other methods of machine learning. Here's an overview of some of the most popular types. Supervised learning algorithms are trained using labeled examples, such as an input where the desired output is known. For example, a piece of equipment could have data points labeled either F for failed or R for runs. The learning algorithm receives a set of inputs along with the corresponding correct outputs, and the algorithm learns by comparing its actual output with the correct outputs to find errors. It then modifies the model correctly. Through methods like classification, regression, prediction, and gradient boosting, supervised learning uses patterns to predict the values of the label on additional unlabeled data. Supervised learning is commonly used in applications where historical data predicts likely future events. For example, it can anticipate when credit card transactions are likely to be fraudulent or which insurance customer is likely to file a claim. Unsupervised learning is used against data that has no historical labels. The system is not told the right answer. The algorithm must figure out what is being shown. The goal is to explore the data and find some structure within. Unsupervised learning works well on transactional data. For example, it can identify segments of customers with similar attributes, who then can be treated similarly in marketing campaigns. Or it can find the main attributes that separate customer segments from each other. Popular techniques include self-organizing maps, nearest neighbor mapping, k-means clustering, and singular value decomposition. These algorithms are also used to segment text topics recommend items, and identify data outliers. Semi-supervised learning is used for the same applications as supervised learning, but it uses both labeled and unlabeled data for training. Typically, a small amount of labeled data with a large amount of unlabeled data, because unlabeled data is less expensive and takes less effort to acquire. This type of learning can be used with methods such as classification, regression, and prediction. Semi-supervised learning is useful when the cost associated with labeling is too high, to allow for a fully labeled training process. Early examples of this include identifying a person's face on a webcam. Reinforcement learning is often used for robotics, gaming, and navigation. With reinforcement learning, the algorithm discovers through trial and error which actions yield the greatest rewards. This type of learning has three primary components: the agent, which is the learner or decision maker, the environment, which is everything the agent interacts with, and actions, or what the agent can do. The objective is for the agent to choose actions that maximize the expected reward over a given amount of time. The agent will reach the goal much faster by following a good policy. So, the goal in reinforcement learning is to learn the best policy. Data mining. Data mining can be considered a superset of many different methods to extract insight from data. It might include traditional statistical methods and machine learning. Data mining applies methods from many different areas to identify previously unknown patterns from data. This can include statistical algorithms, machine learning, text analytics, time series analysis, and other areas of analytics. Data mining also includes the study and practice of data storage and data manipulation. Machine learning. The main difference with machine learning is that just like statistical models, the goal is to understand the structure of the data, fit theoretical distributions to the data that are well understood. So, with statistical models, there is a theory behind the model that is mathematically proven, but this requires that data meets certain strong assumptions too. Machine learning has developed based on the ability to use computers to probe the data for structure, even if we do not have a theory of what that structure looks like. The test for a machine learning model is a validation error on new data, not a theoretical test that proves a null hypothesis. Because machine learning often uses an iterative approach to learn from data, the learning can be easily automated. Passes are run through the data until a robust pattern is found. Deep learning. Deep learning combines advances in computing power and special types of neural networks to learn complicated patterns in large amounts of data. Deep learning techniques are currently state-of-the-art for identifying objects in images and words in sounds. Researchers are now looking to apply these successes in pattern recognition to more complex tasks such as automatic language translation, medical diagnoses, and numerous other important social and business problems. Supervised versus unsupervised machine learning. Data scientists use many different kinds of machine learning algorithms to discover patterns in big data that lead to actionable insights. At a high level, these different algorithms can be classified into two groups based on the way they learn about data to make predictions: supervised and unsupervised learning. Supervised machine learning is the more commonly used between the two. It includes such algorithms as linear and logistic regression, multi-class classification, and support vector machines. Supervised learning is so named because the data scientist acts as a guide to teach the algorithm what conclusions it should come up with. It's similar to the way a child might learn arithmetic from a teacher. Supervised learning requires that the algorithm's possible outputs are already known, and that the data used to train the algorithm are already labeled with correct answers. For example, a classification algorithm will learn to identify animals after being trained on a dataset of images that are properly labeled with the species of the animal and some identifying characteristics. On the other hand, unsupervised machine learning is more closely aligned with what some call true artificial intelligence. The idea that a computer can learn to identify complex processes and patterns without a human to provide guidance along the way. Although unsupervised learning is prohibitively complex for some simpler enterprise use cases, it opens the doors to solving problems that humans normally would not tackle. Some examples of unsupervised machine learning algorithms include k-means clustering, principal and independent component analysis, and association rules. While a supervised classification algorithm learns to ascribe inputted labels to images of animals, its unsupervised counterpart will look at inherent similarities between the images and separate them into groups accordingly, assigning its own new label to each group. In a practical example, this type of algorithm is useful for customer segmentation because it will return groups based on parameters that a human may not consider due to pre-existing biases about the company's demographic. When to use supervised and unsupervised data mining. Data mining techniques come in two main forms: supervised, also known as predictive or directed, and unsupervised, also known as descriptive or undirected. Both categories encompass functions capable of finding different hidden patterns in large datasets. Although data analytics tools are placing more emphasis on self-service, it's still useful to know which data mining operation is appropriate for your needs before you begin a data mining operation. Supervised data mining. Supervised data mining techniques are appropriate when you have a specific target value you'd like to predict about your data. The targets can have two or more possible outcomes, or even be a continuous numeric value. More on that later. To use these methods, you ideally have a subset of data points for which this target value is already known. You use that data to build a model of what a typical data point looks like when it is one of the target values. You then apply that model to data for which that target value is currently unknown. The algorithm identifies the new data points that match the model of each target value. Now, let's clarify that with some specific demonstrations. Classification. As a supervised data mining method, classification begins with the method described above. Imagine you're a credit card company, and you want to know which customers are likely to default on their payments in the next few years. You use the data on customers who have and have not defaulted for extended periods of time to build data, or training data, to generate a classification model. You then run that model on the customers you're curious about. The algorithms will look for customers whose attributes match the attribute patterns of previous defaulters or non-defaulters and categorize them according to which group they most closely match. You can then use those groupings as indicators of which customers are most likely to default. Similarly, a classification model can have more than two possible values in the target attribute. The values could be anything from the shirt colors they're most likely to buy, the promotional methods they'll respond to, like mail, email, or phone, or whether or not they'll use a coupon. Regression. Regression is similar to classification, except that the target attribute's values are numeric rather than categorical. The order of magnitude of the value is significant in some way. To reuse the credit card example, if you wanted to know what the threshold of debt new customers are likely to accumulate on their credit card, you would use a regression model. Simply supply data from current and past customers with their maximum previous debt level as the target value, and a regression model will be built on that training data. Once run on the new customers, the regression model will match attribute values with predicted maximum debt levels and assign the predictions to each customer accordingly. This could be used to predict the age of customers with demographic and purchasing data, or to predict the frequency of insurance claims. Anomaly detection. Anomaly detection identifies data points atypical of a given distribution. In other words, it finds the outliers. Though simpler data analysis techniques than full-scale data mining can identify outliers, data mining anomaly detection techniques identify much more subtle attribute patterns and the data points that fail to conform to those patterns. Most examples of anomaly detection uses involve fraud detection, such as for insurance or credit card companies. Unsupervised data mining. Unsupervised data mining does not focus on predetermined attributes, nor does it predict a target value. Rather, unsupervised data mining finds hidden structure and relation among data. Clustering. The most open-ended data mining technique, clustering algorithms, finds and groups data points with natural similarities. This is used when there are no obvious natural groupings, in which case the data may be difficult to explore. Clustering the data can reveal groups and categories you were previously unaware of. These new groups may be fit for further data mining operations, from which you may discover new correlations. Association. Frequently used for market basket analysis, association models identify common co-occurrences among a list of possible events. Market basket analysis is examining all items available in a particular medium, such as the products on store shelves or in a catalog, and finding products that are commonly sold together. This operation produces association rules. Such a rule could be a statement declaring 80% of people who buy charcoal, hamburger meat, and buns also buy sliced cheese. Or in a less market basket style example, 90% of Detroit citizens who root for the Tigers, the Lions, and the Pistons also favor the Red Wings over other hockey teams. Such rules can be used to personalize the customer experience to promote certain events or actions. This can be accomplished by organizing store shelves with associated items nearby, or by tracking customer movements through a website in real time to present them with relevant product links. Feature extraction. Feature extraction creates new features based on attributes of your data. These new features describe a combination of significant attribute value patterns in your data. If violence, heroism, and fast cars were attributes of a movie, then the feature may be action, akin to a genre or a theme. This concept can be used to extract the themes of a document based on the frequencies of certain key words. Representing data points by their features can help compress the data, trading dozens of attributes for one feature. Make predictions. Data with this feature often has these attributes as well, and recognize patterns. Additionally, features can be used as new attributes, which can improve the efficiency and accuracy of supervised learning techniques, like classification, regression, anomaly detection, etc. Knowing your goals and the appropriate techniques to achieve them can help your data mining operations run smoothly and effectively. Different data is appropriate for different insights, and understanding what you're asking from your data analysis expedites the process for everyone.